We'd like to welcome everyone to another GENI webinar. And my name is Ben Newton. I'm a computer science student at the University of North Carolina at Chapel Hill. I'm a graduate student, actually just hoping to graduate this semester. So writing my dissertation and everything right now in the midst of it. I want to just let everyone know that the next webinar is going to be February 23rd. And we have Nick Bastian is going to give a presentation on GENILib. So kind of look at that. Keep an eye out for emails about that. It should be a great webinar to learn about GENILib. And now it's my pleasure to introduce our presenter for this webinar. She received a PhD in 2007 from NC State University. We won't hold that against her. A rival of Chapel Hill, where I'm a student. She worked at IBM on their WebSphere application server and did a postdoc looking into the performance on disk drives, and has worked at a couple different universities and is now an assistant professor at the College of Charleston. And in addition to all of that, she's also actively working with GENI and especially doing some security research using GENI. And it's my distinct pleasure to turn the time over to Ksenia Mountruidu.
Well done, Ben. So thank you very much, Ben, for the very nice introduction. So I will share my screen right now so that, am I already sharing it or?
It doesn't look like it.
Okay, so I will share the screen now. And I believe it is shared now.
Yeah, I can
thank you very much. I'm Ksenia Mountruidu. As Ben has already done good rehearsals and he said my name very well. And students call me Dr. X. It's so much easier. But Ben wanted to try to say the whole thing. And this presentation was supposed to be done with my undergraduate student, Blaine Billings, who is a freshman. And he also helped me prepare this live demo. However, unfortunately, he's falling down with a cold, so it was better for him to stay away from me as well. So we're both from the College of Charleston, a liberal arts school in Charleston, South Carolina, and I think that this is a good time to start and to preface this presentation. This has been, as fun projects are, a nice collaborative research with Johns Hopkins University, Dr. Sean-Young Lee from Johns Hopkins, and a student then that has now graduated from Rochester Institute of Technology, Tommy Chin, and his advisor, Dr. Kai-Chi Xiong from University of South Florida. So this work started as a collaborative research. It has been presented in a couple of conferences, and in my talk, I'm going to give you some background of our work on GENI. Like Ben said, we're quite active. I have a research group of undergraduates primarily, and one graduate assistant right now at the College of Charleston, and Johns Hopkins and USF have a lot of work on GENI as well. I'll give you some motivation on the research work that I'm going to present, the detection and mitigation of denial of service attacks using GENI experiments. I'll give you the methods on our collaborative detection methodology, the details of that. I'll talk extensively about the implementation. I like that because it gives me the opportunity to discuss to you about our code, which is also publicly available, and you can replicate our experiments on GENI. I will do a live demo, which hopefully is going to work. Even Bill Gates has had issues with live demos. So I have to say I've tried it a few minutes ago. It works, but we shall see. I also have a video demo, so that should be fine. My student would be doing the live demo so that you don't have to watch me all the time, but like I said, he's not here. And then I'll give you some conclusions and future work. And I hope that this is going to bring a good conversation or even new collaborations. And it may inspire you to use GENI as well in security experiments. So the background and a little bit of a story. So this, our work started as we met at a GENI workshop, actually, Dr. Lee and Dr. Xiong, and we found common research interests, and we started working on denial of service detection and mitigation using SDN on GENI. It has now blossomed to more research projects. I'm going to mention these. Of course, there's not enough time to talk about all of them. On covert storage channel detection, covert timing channel. Currently, we're working on cross-site scripting, moving target defense, and firewall implementations. But besides the research, what was really cool that came out of this was also education modules and education experiences. So, and that led to a funded project, an NSF funded project that we've got right now that is called CyberPaths. It's cybersecurity paths for students in the liberal arts. You may know that College of Charleston is a liberal arts college where students have to take a large general education core. So besides the technical GENI cybersecurity modules, this project also includes liberal arts inspired modules such as law, cyber insurance, hot topics like that, privacy, finance. The two things I'm going to talk about today are, of course, the denial of service research and the GENI cybersecurity modules that, this is what my live demo is based on. But if you want more information, I have this at the end of the slides, and Ben has nicely put this in the on the GENI website. So, so to start with the motivation on our research in denial of service. So you probably know that denial of service is an old attack. However, it's still coming up. I mean, a couple of months ago, the Mirai botnet brought it back to the spotlight. A very interesting attack. The code is out there. I've got it downloaded. And to me, it's very interesting that we haven't seen the end of denial of service. The Mirai botnet even introduced a couple of variations, kind of new denial of service attacks. It's shaping differently nowadays. It's mutating with all of these interconnected devices. So it's kind of job security, but also it's getting bigger and more, I would say, worrying to researchers. It also has a huge financial impact. So a few data that I gathered, like, one daunting statistic is that half of the world's enterprises have been affected by denial of service, according to Dark Reading in 2014. It's also very easy to buy on Darknet. So, it's offered as a service right now. So it's a good reason to study it, to still study it, and still try to improve the detection and the mitigation techniques for this type of attack. And the computer networks today, as I said, are mutating. As you probably know, there's a lot of data that we have to process nowadays because of the Internet of Things, even more data to analyze, and the topologies are getting more complex. Our motivation was also software-defined networking. So GENI is a great paradigm and a really nice sandbox for SDN experimentation. I know, and I see that lots of researchers are using it greatly. For us, it was about leveraging software-defined networks to create security solutions. So what we leveraged were the actions, the things that you can do with software-defined networks, this nice separation of control and data layers. We used this programmability to drop malicious flows or redirect them to a honeypot, or even duplicate the flows to a monitor. And also the great thing of having real-time access to the flow table and having this big picture of the network, that is very school for security research and leveraging SDN for security. Now, of course, there's a body of work in denial of service SYN flood. There are also known solutions. I'm not going to go through the whole related work, but I'm going to mention it as I go. So there's well-known solutions. There's Yelena Mirkovic's work at ISI, UCI, and lots of work on this aspect. Our work is also focusing on leveraging SDN for security. So there's an interesting body of work in that area as well. So for more information, you can look at the publications that I'm referencing. I'm going to give a little bit of background, even though the TCP SYN flood that we used as a sample attack is very well known. I'm going to give some background on how it works. And I say that we use it as a sample attack because this can be a generic solution that we're looking at expanding to other types of attacks. But the SYN flood, what it is, so it's based on perverting the TCP three-way handshake. So as you know, the three-way handshake is very nice to establish a connection. A client sends a request, a SYN request, the server replies with a SYN ACK, and then the client replies with an ACK, and the connection is established. Now the SYN flood is perversion of this three-way handshake in terms of the client, in this case the attacker, is not replying with a third ACK, so connections remain open, which can deplete the server from its memory, or by flooding really, really fast, it can even run out of bandwidth and before that. But not only that, not only open SYN connections are part of the signature of the SYN flood, but also part of the signature could be spoofed IP addresses. So there's tools that an attacker can use to fake the IP address of where the attack is coming from. And as you can see in that diagram that I'm showing, the attacker is using a spoofed attack. So the SYN packet goes to a server, the server replies to the spoofed client, and of course the spoofed client is ignoring this SYN ACK because it never sent a SYN to start with to establish a connection. So so this is another variation of the SYN flood attack. Actually, the traffic that the spoofed client receives has been extensively analyzed with the backscatter data and the telescope data, which I think it's UCI, but I'm not sure. So that's a description of the attack that we chose, a nice sample attack to use for our prototype and implementation. So as we were looking at this, we looked at the challenges. So as you know, intrusion detection systems are very imperfect. So an intrusion detection system is based on attack signatures. Now, of course, and I'm doing some work in machine learning for intrusion detection systems, not in this specific paper, but there's better ways of not base your intrusion detection system in just an attack and just a threshold. There's better ways, behavioral analysis and all that, but still, an intrusion detection system, its data availability, it's limited. It's limited, and it's really based on where you put it in a network. There's not a perfect spot. There's some good spots to put it, but location matters very much. So furthermore, the other challenge in our implementation was the software-defined network controller. So there's a researcher at Texas A&M, Dr. Guofei Guo, that is doing work in security for SDN, which is different than the way we are using it. We're using SDN to establish security. So he has also looked at attacks to the controller. The controller is a bottleneck, especially when a denial of service attack is happening, it can get overloaded. So furthermore, if one wants to leverage the controller information to analyze every packet, and that's what we wanted to do, we wanted to leverage the controller, the smarts of the controller, then then the controller can be a big bottleneck in this type of implementation. And again, the controller's efficiency also depends on its position on the network, for how many switches it's controlling, and all of these different factors. Finally, in this type of work, there's always a trade-off between accuracy and performance. So you may trade one for the other, and that's always very interesting, what one is willing to sacrifice. And one of the things that we found that was really lacking when we were reviewing the related work was a real-world implementation of this leveraging SDN for security solutions. So we found a lot of mininet implementations, which has its own limitations, but it's a very good simulator. And also we found a lot of thesis papers, but not a real-world implementation with GENI. So our solutions in this research were, number one, we would keep it simple in terms of the intrusion detection system. So we decided to keep this simple. We decided, but we decided to use as much information as we can about the signature of the attack. So part of the signature was the increase in SYN packets. That would be the simple feature that the intrusion detection system, that our intrusion detection system observes. And part of the signature is the spoofed source IP addresses. And this is where we leveraged SDN and used the information of spoofed IPs to confirm that there is an attack or that there is no attack, and to also figure out where the attack is coming from and block it, drop the rogue traffic. The other part that we used was distributed intrusion detection systems. So since we had GENI and we were able to reserve a load of a nice bunch of virtual machines, we were able to distribute our monitor devices, and we were able to use communication of our monitors. We created actually a small communication protocol between our monitors and SDN controllers. And then the other part of our solution was SDN. We used the programmability of the OpenFlow virtual switches to add and remove flows, to duplicate flows to our dedicated monitors. And then we also use the flow table in combination with the spoofed IP addresses. And of course, GENI was an integral part of our implementation. So I'm gonna stop over here. Do we have any questions or? So I'm gonna start now getting a little bit more into the protocol of our implementation, and the key ingredients to the implementation are three different agents. These can be different devices, or they can all run on the same device. So these three different agents are the monitor, the correlator, and the controller. So, like I said, we can locate these in the same machine or different machines. In our implementation, we have the correlator and controller agents on the same virtual machine, and the monitor in a separate virtual machine to have this distributed processing, as I mentioned. So what's happening with the monitor? The monitor is running intrusion detection software, and what's happening with that is that if it notices an increase in normal traffic, the monitor will send a message to the correlator, that agent that is working in a separate virtual machine that is also running a POX controller, Python-based controller. So the correlator takes that message and it's processing it, it's correlating it with the flow table information that it gets from the controller. And in this first case, it finds that the increase in normal traffic was just a normal increase, an influx of traffic, what we call a flash crowd or something like that. There's nothing wrong with the traffic. There's nothing wrong with this increase. So it sends a reset message to the monitor to reset the threshold, increase it a little bit so that it's not that sensitive to the increases in traffic. Now, in the case of an attack, again, the monitor keeps monitoring, and in the case of an attack, the detection stage starts, and the monitor again sends a message to the correlator. The correlator queries the controller. It asks for some information, and I'm going to get to the details of this information and how this information gets correlated. But for now, it asks for information. The controller says, yes, based on the information, the attack is confirmed, sends a message to the correlator, and at the same time it mitigates, it blocks the port of the OpenFlow virtual switch that is where the attack traffic is coming from. And then again, a reset is happening. The threshold is not updated, but a reset is happening, meaning that everything is set, the attack is mitigated, and you can now continue on monitoring. So this is the kind of the big picture of what we're doing. Here I'm showing them the actual topology that we used in our research. In my demo, I'm using only one OpenFlow virtual switch and very few nodes. But in our research, we had 30 hosts, three local networks. Each one had 10 hosts that we could use as attackers because we were doing distributed denial of service. And then we also had in each local network a monitor, a correlator controller. Like I said, this was the same virtual machine that was running POX, the POX controller, and our correlation scripts. And this one was for each network, and then we had a backbone. So we were emulating a small enterprise, small campus, or small enterprise, small company network. So again, because I said that I will show you also the communication protocol that we have created, I'll show you a little bit of the sequence of events. So we have a client that is requesting content, web browsing, or something like that. The OpenFlow virtual switch that gets this request and then communicates with the controller in this case. And in this case, the controller says, this is a new flow. Let's insert that new flow in our flow table, and let's continue on. In our experimentation, we're also using the OpenFlow virtual switch to mirror traffic to that dedicated virtual machine/machines that are our monitors. And eventually, pretty fast, all of these things are happening, of course, pretty fast. We forward the traffic to the server. So if that traffic indicates an influx of traffic, the monitor is going to send an alert to the device that is running the controller/correlator, and the correlator in this case takes the alert and the details, correlates, queries the flow table, and then it will take action accordingly. So the correlator will tell the controller either continue on, keep this flow, or drop this flow. So I'm going to stop over here just in case we have any questions. As you can see, I have kept a note to ask you if you have any questions. So I'm going to continue with the monitor right now. So what the monitor is doing, so our monitor was running a standard intrusion detection system, snort. We created a custom, very simple alert. In our case, we only wanted to look at the number of SYN packets per second and influx of SYN packets per second. We experimented with different thresholds. We have some ROC curves, receiver operating characteristic curves, where we improved our accuracy. But that was the simple task of the monitor. Listen for SYN packets. If the alert threshold is violated, then send an alert flag to the correlator, which is a script that is running on another device. And with this alert, also send IP addresses of the SYN packets, IP addresses of SYN packets to the correlator. And keep doing this, keep sending IP addresses. So I'm showing a little code, since this is about experimentation and implementation. And like I said, this code is free. We don't have it up on GitHub yet, but we will very soon. But it's free open on the website that I have at the end to look into. So what the monitor is doing is it's reading snort logs. So our monitor Python script is processing snort logs in real time, so that's tell and seek, it's real-time reading of these files. And if we see our custom alert, if we see our custom code and alert that the threshold of the SYN packets per second has been violated, then the alert is going to be sent. And here I show how we send these alerts. We're using a system call, we're using netcat to send this information, and we're sending a whole file with information, and the information is the alert, the type of the attack. It could be any information, but like I said, we're leveraging the spoofed IPs in this specific attack, so we're sending source IPs that belong to SYN packets. And these are all sent to the correlator, which is another Python script that is running on the same VM as the controller. So now here is the how the correlator is working. The correlator initially has a snapshot. It uses the OpenFlow API to get a snapshot that it saves in a hash table with using as key values the ports and values of the hash table, the IP addresses. It has a nice hash table of the original flows that are running, original flow traffic that is running in that local network where our OVS and our controller is running. Now, when the attack happens, like I said, IPs are getting sent, SYN packet IP sources are getting sent to the correlator. The correlator now queries and takes another snapshot of the flow table, and it looks for the IP address of the SYN packet that it has just received. And it finds that it comes from the same port that it used to have a different IP address before, when regular traffic was happening. Now again, another IP address is sent. So like I said, we're sending multiple IP addresses to the correlator. So a second IP address is sent. So in a matter of a very few milliseconds, 2 IP addresses or more are sent to the correlator, and the correlator takes snapshots and sees that all of these IP addresses are coming from that same port, and it's a matter of time that, very short amount of time that these IP addresses are hitting the same port. Now the correlator knows that this port is not the backbone port, so we have this backbone port marked, and it knows that this cannot be happening. So after this cannot be happening, we cannot have all of these IP addresses coming from the same host in a local network, all of these different IP addresses. So this is how we leverage the spoofed IP part of the signature of the SYN flood attack, and we use this nice flow table information to say, yes, this is a spoofed SYN flood attack. It's coming in from port 2. This is probably an insider that has been compromised, and we're going to block them. So going back to the picture that I showed you, the correlator that would be doing this is this correlator. So it would be blocking its own local device. And of course, this backbone link would be whitelisted. So I'm going to show just a little bit of how this is happening. Like I said, the correlator is running queries, open flow queries. So dumping the flows, getting different snapshots in time, and an original flow table snapshot, and multiple snapshots in time as IP addresses are received. And then what's really nice is that parse function, which we try to make this as fast as possible, because as you can understand, there's an influx of information. The flow table is growing. Our search would be slower. That's why we used hash tables that we have almost constant time of searching for these IP addresses and verifying, correlating that there is an attack, and finally mitigating. So just for clarity, we split the mitigation to 2 Python scripts. So the mitigation script, just for clarity, and because we wanted to do more distributed work, like let's say the mitigation, the controller could be running on a separate VM than the correlator scripts were running. So we call the mitigation once we verify that from this specific port we've seen different IP addresses, and this looks like rogue traffic. So just for separation of concerns, we split the mitigation script, and the mitigation script is called, and what it does, that's the lower part of my screen, is it's sending to the switch an action, an open flow command, an action to drop the flow from that specific port. So that's what's happening in this correlation and mitigation technique that we have implemented on GENI. And as you have probably realized, the role of SDN is integral in our implementation to duplicate flows in our monitor virtual machines, to get flow table information that is valuable and it can be leveraged very, very well, and to drop flows. In our case, we drop the flows, but one could also redirect the flows to a honeypot for further verification that this is actually an attack and not a flash crowd, and for further investigation. So if we don't have any questions, I'm going to show a video that we've got from the larger topology experimentation. I'm not going to do a live demo with the topology that had 3 local area networks. I'm going to do the live demo with a smaller topology. So then I'm going to do a live demo.
Kenya, I have a question actually.
Oh yeah, sure.
Is there a reason why you chose to use snort versus other intrusion detection systems? Was it just was there some reason for that, or was just that was the easiest?
That's a great question, actually. So truly that was the easiest. We were more familiar with snort. It was easy to write an alert. We thought about using Bro or Suricata is being used very much right now. This is a really good question, and it would be interesting to look at another IDS, or maybe running different IDSs, because we have 3 different IDSs running in our research topology. So having, Bro and Suricata, and see, if we would have maybe more sophisticated alerts or faster reaction or better reaction. So there was no special reason to that except familiarity. So thank you. That was a good question.
I also have a question.
Mm-hmm.
As you said, just looking at the flow tables, it is possible to detect a DDoS attack. So how does monitor fit into this place? Maybe we can run an analyzer, flow table analyzer on the controller without using a monitor. This is one of my questions. And the monitor you are using is an IDS system. Can it be possible, just looking at the telemetry data, something like packet samples or just packet headers, could it be possible to detect this kind of TCP SYN flood?
Okay, so let me answer the first question. So this is a very good question. Actually, we have considered that there could be other methods, like you said, a flow table analyzer or any other monitoring mechanism. Again, we wanted to use something that was well accepted and out there. I mean, snort is being used by industry and academia. You're definitely right. That was one of the thoughts that we have had, also having the monitor running on the same device, all three, monitor, correlator, and controller running on one VM, not having to have communication between the two, which I showed was happening with Netcat and all that. That could save some overhead in the communication. However, on the other hand, monitoring is quite a task loading. It's quite a CPU loading process. So distributing it to another virtual machine that saved us from bottleneck from loading our controller even more. Can you repeat your second question, please?
The second question is that, for example, I am working on a project that collects packet samples from switches in the format of S-flow.
Mm-hmm.
And just looking at these samples, I'm trying to figure out if there is an DDoS attack. There's another method. In the second method, they collect packet headers, only the headers, not the packet contents. Then in this second method also, we are trying to figure out if there is a DDoS attack. The second method is using NetFlow telemetry. And S-flow, the method you have used, is actually looking at the contents of the packets, level packet payloads. This is something expensive solution, expensive way of monitoring. Could it be possible to make it cheaper using telemetry data to detect this kind of DDoS attacks?
So that's a good question. So actually, we are using, I mean, we're mainly using packet headers as well. We're not looking really at payloads. We're looking for SYN flags and IP sources. So the monitor is only taking these. And actually, when I show you the live demo, you'll see exactly how it's done. Absolutely, the less that you analyze, I mean, the better the performance is going to be. So maybe that can be a good improvement for sure. Not looking at payloads, just looking at headers. We're not really looking at the inside of a packet. We're just looking at SYN flags and all that. And like I said, we did use snort. We didn't do a custom solution. So if there might be a better way with another method that is more lightweight, for sure it could help, because as you will see, the performance is pretty good. However, there is some work to be done to scale that up. So as you can see, as you will see in the results that I'm going to show, we have a small network, and still we have some delays by using snort and communication and all of this. So absolutely, something more lightweight can make this better.
Thank you.
So do we have any other questions? These are very good. Let me show, then I'll get to that video that I've got over here. This has also been shown in a GENI GEC, a GENI engineering conference. All of this is run on GENI, by the way. You can see a root terminal. We were able to get something like a remote desktop on GENI, and this remote desktop is running a tool called Organic IP, OIP. So you can see that at the bottom left of my screen. And this tool is a really nice visualization that shows what's happening. In the beginning, there's the normal traffic, and then there's this influx of spoofed IP addresses, and the circles indicate traffic, volume of traffic in a node. So this is a really nice, very nice visualization that was presented at Usenix. You can find the paper, Organic IP. So I wanted to show that in a video to visualize what's happening. So we are running over and over again our detection and mitigation. So as you can see, when detection and mitigation is happening, again, the normal traffic, the traffic drops, and that's where our detection and mitigation is taking place. So this is a continuous loop that is showing an attack and then dropping the flows of the attack. And actually this attack was coming from multiple nodes, so we were blocking multiple ports in these 3 local area networks that we had. So this is a demo that we did at GEC 22, and we also got the Best Demo Award on this one, so that was pretty cool. And now it's gonna be live demo time. So I am going to actually take the screen maybe. So I have my terminals over here. I have 2 terminals open on the controller / correlator, 2 terminals open on the monitor, and then a terminal open on the victim, the attacker, and the user. Let me show you the topology. So over here, I'm running GENI desktop. So the topology is, like I said, for the live demo, is much smaller than the actual topology that we used in our paper. It's just a single OpenFlow virtual switch, monitor, controller, and the 3 nodes. So it's not even a distributed denial of service, it's a denial of service, single attacker. But it's a cool demonstration, and what I want to show is the links that I also have, we also provide. This is how you can set up this small experiment, and then you can scale it up. I mean, there's nothing too difficult to scale that up. I use these instructions in my undergraduate classes, and they're very detailed, and definitely you're very welcome to use these to set this up. And then so the first parts are the setup and setting up things with GENI desktop. We also have the students set up an OpenFlow controller. It's very nice because we can talk a little bit about SDN. And furthermore, we have the students install snort and configure it. And then configuring the OpenFlow virtual switch. Again, very nice experience for undergraduate students. And I mean, even graduates. With graduates, you can make this, if you want to use this in class, you can make this more open-ended and have the students figure out how to set up things. There can be very nice variations. And then we have the students run an attack manually and observe the traffic and write their own custom rule. The correlation is also where I have I link the correlate Python script that I also showed you the code, the analyze Python script, which is really analyzing snort logs and communicating with the controller / correlator. And so what I'm going to do over here is I'm going to run everything. I'm going to run all of the whole experiment, detection, correlation, and mitigation. So I'm going to start the POX controller that, as you can see, is duplicating. It's duplicating flows to the monitor. So, let's see. Okay. So it seems like my terminals have kicked me out. So let me minimize that. So I'm gonna have to reopen these. That's what happens with real demos. I was hoping that these were going to, I'm gonna have to reopen these. It's pretty easy. I think I had them open for too long. So.
While Ksenia is getting those new windows open, let me just mention something to the people I was going to say at the end. In addition to these webinars, Jay Ikut and myself, every semester, we host a GENI in the Classroom seminar, which is just a 2-day online training for anybody who is interested in potentially using GENI in their classroom. So if you're a graduate student TA in a class, the networking class, or if you're a faculty in a networking or distributed systems class or anything of the sort, and that sounds like it's something that you might be interested in, send me an email or be on the lookout for those announcements on the GENI lists. I think I'm going to send out another one today. But you know, either yourself or your TAs or could participate in that. It's essentially a 2 hours, 2 different weeks. So there's one a week from today, which is kind of an introduction session. Even if you don't know anything about GENI, you're free to attend that, and we'll kind of walk through all of the GENI information. And then the second week, so it will be 2 weeks from today, the 10th of February. And that seminar, we kind of get more in depth and talk about tips and tricks for using GENI in the classroom, and talk about how you can, what works well and what doesn't. And so those are just 2 kind of an advertisement for that. So this is GENI in the Classroom. A seminar starts next Friday and continues the following Friday, each 2-hour sessions on those Fridays. And my email is in all of the emails you've received about this webinar. So you can email me if you're interested, or like I said, the GENI mailing lists should also have this information.
Okay, thank you, Ben. You filled the time very well as I was getting back all my terminals. So I've got everything ready now, and let me pull the GENI desktop as well, because this is kind of time critical to see for the live demo. So here are the graphs. So these graphs are showing the traffic on the victim device, the total traffic on link 2, which is what connects the victim device to the OpenFlow virtual switch. And as you can see, this is low traffic, and if I am lucky and this shows well, I'm going to be able to show you an influx of traffic and then how it gets mitigated. So let's see if this is going to work. So first I'm going to start the POX controller, make sure that it's connected and all that. And like I said, you can definitely replicate that experiment. This is a small subset. It's not a large experiment that we did in our research. And you can expand from that. And then I'm going to start this. I'm going to start snort, make sure that this works, and monitoring. And it also has our custom simple rule. Then I am going to start iPerf server. This is just again for demonstration. We were running different loads for regular traffic. In this case, I'm just running iPerf just to run some load. And then I'm gonna start a script on the monitor, which is the analyze Python script, which I showed you this code. This is the one that is analyzing snort traffic. Then I'm going to start the correlate script, that is the one that is receiving alerts and IPs and queries the flow tables and all that good stuff. And now I am going to start the regular traffic, which shouldn't do anything. And then I use hping to run an influx of traffic. And as you can see, correlation and mitigation has already happened. Now, GENI desktop is not gonna catch up that fast, so it's gonna take a little while, but I saw this and it was so GENI desktop is a great tool, but of course, you know, now I have a lot of things happening in my network. But one port was blocked, port 2, and you can have the students verify, or if you're using this in your research, you can check, is this actually the port where the attack traffic is coming from? I have left our debugging logs to come out, so you can see that the analyzer, besides reading alert logs that are text files, it's also reading the TCP dumps from snort, and this is happening pretty nicely, pretty quickly. And now GENI desktop, here's what's fun with GENI desktop. As you can see, the order of magnitude of the traffic has increased. So the previous traffic, the regular traffic, is this little, you know, line. Actually, it has become a flat line, and this is when I was running the denial of service attack, and eventually you will see that this is getting blocked and actually mitigated. So I hope this is gonna come up really quickly. I wanna show, the last couple of things I wanna show are some results that we had from this research, accuracy and performance results. Like I said, there's a lot of good improvement for this method. By the way, to run these experiments, because we had a larger topology, we created an automation script that was not doing the things that I just did manually, that was doing the things that I just did actually manually. So it was logging on to nodes and starting snorts, starting the analyze Python script and starting the different scripts. So as you can see, the attack lasts for some time, but eventually it's going to get mitigated. So let me see, I don't know if I can make this. So I can let this run and show you in a little bit, but I think this is the point that mitigation happened. I don't see any other spikes. So this is exactly the point that mitigation happened. So the traffic keeps going, but the port so there's still traffic from iPerf, which is very, very low, but the denial of service has been mitigated. So the results were interesting when we were running this and we were increasing the number of attackers with the larger topology that I showed you. There was a standard increase in the delay for us, for our detection and mitigation time, a few milliseconds. But the interesting part is, after 8 attackers, we had some decrease actually in the delay, which actually plateaus, an increase in our delay. And this is because of that huge influx of traffic when we had 10 nodes running hping 3, all going to the same victim. And hping 3 is pretty high traffic, pretty good simulation of a flooding attack. So that's pretty good and pretty promising. Like I said, there's still work to be done in scaling up, but in terms of accuracy, the results were very good because we were running only one attack, of course, in the network, and this here I'm presenting our receiver operating characteristic curves on different monitors, monitor 2, monitor 3, and you can see that there's high true positive rate and the false positive rate is quite low. Again, this was run with only one attack, with only that SYN flood attack, and regular traffic, Apache Benchmark or iPerf. These were the two regular traffics that we used. The one thing that we would like to do is vary a little bit the regular traffic. We are using tmix right now in our new experiments, so this would be great to use in the denial of service experiments. So that's one thing, but even though it's really good, the accuracy, it kind of makes sense because we have a specific signature and we are verifying it using two data points. One is our monitor and the other one is the flow tables. So that goes to show that if you have a couple of ways of verifying what's happening, the accuracy of your detection can be very good. Now, again, the future work is definitely scalability, definitely different loads, and we have almost completed the work on covert communication. So I'm gonna show you just a couple of things. We have actually presented that work at the National Cyber Summit, the covert storage analysis on GENI. So this is more security experimentation that we're doing on GENI. We're doing everything we can, except of course worms and malware. This is not the place to do this. One can use DTER lab to run worms and malware. So my student is presenting at a research competition, undergraduate research competition, a covert timing channel implementation on GENI. And what's really cool with this implementation is that it's done with stitching. So we had a very nice, very realistic covert timing channel with some error rate, but we have different methods of mitigating for the error rate of our covert timing channel. And then we are developing new modules for education. So our research is feeding education. So, if we're researching, let's say, firewalls, we're going to also make a nice module with instructions on how to implement the solution on GENI. And then Johns Hopkins has got a very good work on, and a couple of modules that are going to be coming up and are on cross-site scripting and certificates and authentication. So this is the future work. So keep checking these websites, and we'll probably be sending emails if you want to see more experiments that you can use either to expand in your research or in education. And finally, okay, of course, we have to acknowledge NSF that is funding the education research, and also GENI. Like I said, this started, the collaboration started at the GENI workshop. So, to me, I still meet great people in the GENI workshops and get new collaborations. I mean, recently I also had a couple of people that I'm still talking about on research. So these are great venues. So I have more results if you would like to see from our work, but I'm gonna wrap this up right now, and I'm happy to take more questions.
Ksenia, there's at least 2 questions in the chat window about code. People want to know where they can access the code. Is there a URL for that, or?
Yes, and actually, okay, the organization of the URLs is not very good. So I'm going to give you the URLs for the code. Yes, where you can download and use it. I'm going to provide this. So this is actually, I can show you over here. So this is in the, I have linked this site, the CyberPaths site, which is our education site, and you can find all 3 Python scripts over there. You can also find our RSpecs. We're working on improving our instructions, so we're going to put these links also on our instructions, but for now, you can find it in this blog CyberPaths modules, so there's all the code.
I just put that in the chat window too, so I assume
Perfect.
I assume I typed it right.
So I can copy paste it as well. Yep.
What other questions do people have for Ksenia?
I have another question. How did you send snort alerts to GENI? Is there an interface for this, or did you write something for that? How was the correlator aware of these alerts?
Okay, so let me see if I understand the question. So how did I get the snort alert? So I didn't use an API interfacing with snort. What I used was I wrote this analyze.py actually. The crappy code is partially mine. So the analyze.py is reading text files and TCP dump files, and the alerts are sent from one node to another using netcat and simple, netcat communication. So if I understood your question correctly, so what the analyze script is doing is it's reading two sets of files. One is the text file alert that snort is creating every time there's a new alert, and then the other set of files is TCP dump logs, and all of these logs are saved in var log snort. Then the alert.py is opening a netcat communication with the correlators slash controller, and it's sending this alert information, for example, SYN-FLAD, together with IP addresses. Does this answer the question?
Yeah, that was my question, and you answered it. Thank you.
Somebody just put a question in the chat window. How do you distinguish SYN flooding traffic from normal traffic?
Okay, that's a very good question. So this is an imperfect way of distinguishing SYN traffic. So like I said, in our case, when we saw an influx of SYN packets, we assumed that this might be an attack. Now, again, this could be a flash crowd trying to connect to the, let's say, Apple website because the new iPhone came out and all that. So the second part was to use the IP addresses, all of these multiple IP addresses coming from the same port that, and that was the spoofed IP address signature, that was the fishy part. Now, we actually, for the accuracy, we used flash crowd traffic, and we had some reduction in our accuracy because, again, because we are using just a simple threshold of SYN packets per second, there was no way to say that, these high surge of SYN packets per second are flood traffic. So it's really an imperfect way, but together with the information of the spoofed IP addresses for the denial of service, where spoofed IP addresses are part of the signature, that has worked very well. And like I said, again, this can be a really good way of self-policing a network. So really the blocking was happening on the individual. Let me find the slide actually that shows the topology. So the blocking was happening in the individual network where the attack was coming from. So maybe a node on network 3 was getting attacked, but the monitor that observed the attack and that was blocking this specific client that was rogue, compromised, and was sending spoofed SYN surge to network 3. So this mitigation can work really nicely if you have, let's say, a campus network and you have so many devices, or Internet of Things devices, or whatever, your PCs that may have gotten compromised, and they're getting used by somebody as a botnet. So if somebody is takes our code and uses this can be a solution of self-policing. Now, for your network that is being under attack, all you can do is say, I'm getting attacked through that backbone link, but you're not going to block that backbone link because there could be other traffic. One of the ideas that we had is, what if this was the same organization? We could have monitors communicating with monitors, or monitors communicating with other correlators. So there's lots of variations, and that can happen. So does this answer?
There's a follow-up question, I believe. It says, in your recorded demo, how do you identify the dynamic green dots? Are they determined based on the common network numbers?
So, and now it's has come back to, so the green
I think
dot.
they're referring to the organic IP.
Okay. Sorry about that. So the recorded demo. Sorry about that. So the green dots. So the green dots, I think they correspond. So I'm trying to remember now. I think they correspond to the nodes that are coming up. The green dots correspond to our. There's I think this, and I would need to go back and look at the details of OIP, but I don't think there's a way to say, okay, this green dot belongs to the host 10.10.10.23. So I don't think there's a way, but they do correspond to the specific hosts that are coming up right now. And if I keep this rolling, so this big green dot, I think this is the traffic that is going to one single node, and then these indicate new flows. Again, I would have to get back to this and see. That is a very good detailed question of the visualization. So these green dots may be new flows coming up. So that's a really good one. And I'm not going to say that's perfectly right, what I just said. I would need to go back and look at the details. So, but I think these correspond to the GENI hosts that are getting an influx of traffic, and you can see more small ones. These to me look like different flows. Just reverse engineering it now and not remembering what OIP is doing. This one is total traffic that we are monitoring on the victim. So this one I know, and then the IP addresses that are coming up on the network.
There's one more follow-up question, it looks like, too. So whenever an attack happens, and we probably mitigate it, can't the attacker be aware of that the attack has now been terminated? Is there anything you have already looked into it with?
So can the attacker be aware? The attacker is not aware that that the attack is mitigated. So so we don't. So thinking about this, so by dropping the flows, especially, the attacker is also spoofing IP addresses, so it's not really verifying. It's not able to see if the attack is going through or not. So that's one thing. And I'm not sure if I understood very well the question, but I think, no, the attacker cannot see this. The network now can, so the correlator, the network can see that the flows have gone down. So the correlator is going to send a message back to the monitor. This has been blocked. And reset your threshold and clear your buffers, or start another TCP dump. So this is what exactly is happening. We say start another TCP dump. So there is a last communication after we drop the rogue traffic between the controller, correlator, and the monitor saying, just, you know, everything is set, we blocked, don't send me any other IPs on that, and just reset, start a new TCP dump, and start new alerts. So these two are able to figure that out, but not the attacker. So does this, let me see if I can see the chat.
Thanks, that answers the question, he said. That was Roshan. Other questions? Okay, well, thank you again to Ksenia for presenting today. It was been great to see what research you're doing in the security area. I think this is a very diverse set of different videos that we've made and webinars that we've hosted, and I think this is the first one that's been security related. So thank you so much for that, and thank you for everyone for attending.